Hello and welcome back to our video series on statistical methods and data analysis. In our last video section, we discussed describing distributions of variables, and we looked at numerous ways we could do this. In this particular section, we're going to look at describing relationships between two variables. Now, in order to describe a relationship between two variables, the first thing we need to do is create a scatter plot for our graphical description. Now, our scatter plot is useful when we have two variables present. We can determine if a relationship exists between these two variables. So here I've got my x-axis, here I've got my y-axis. Now, in order to determine if a relationship exists between two variables, we need three things we need to describe: direction, form, and strength. So what is the direction of our relationship? What is the form of our relationship? And how strong is our relationship? For our direction, well, we've got positive and negative. Here I've got positive direction. I've got a positive slope, and a positive slope is positive direction. If my slope, on the other hand, were coming down from left to right, then I would have a negative direction. Form. There's linear, there's nonlinear, and these include x squared, exponential, or logarithmic forms. There are many different linear possibilities. Here I've got perfect association. Every x variable is perfectly associated with every y variable, but notice, this is linear. Here I've got nonlinear. Notice, this is a parabola. This is x squared. This does not mean there's not an association. This means there's not a linear association. So this is nonlinear. Here I've got exponential. Notice this is an exponential curve. Again, there's an association. It is just not linear. Here I've got logarithmic. This is a logarithmic curve. And again, there is an association, but it's not linear. Strength ranges from none to perfect. And this goes with negative or positive directions. So I can have perfect negative strength. I can have perfect positive strength, and so forth and so on, until I get down to no strength at all. What defines this strength in our scatter plot? Well, here, all my x values are perfectly associated with all of my y values. So this strength is perfect. Here I have strong. X and y are related well. They're not quite as good as perfect, but we should give further investigation to this strength. Moderately strong. Notice, the scatter around my trend is beginning to get wider and wider. There is a relationship, but it's slightly less reliable. But we probably should investigate this. Moderate. Notice the scatter is now even wider. My relationship exists, but my reliability has once again decreased due to a wide variability in my trend. Moderately weak. Again, variability has increased even further, and it's possible, but it's kind of difficult to determine if a relationship exists here because there's very weak strength. Weak. There's very little relationship at all between the variables, and we can see we can't tell where our trend is. And then no strength. There's no relationship that exists between these. We can't draw any inference. We can't make any statements, including, well, it's kind of difficult to even say what the direction is. We will discuss methods in which, given a scatter plot such as this, we can at least determine the direction. We also need a numeric value that tells us what is the strength of our relationship. And in order to get this, we're going to use what's called the correlation coefficient. Pearson's correlation coefficient, it measures the strength of the association between two variables. If you have not watched the video on standard deviation, you should do so. The correlation between x and y is the sum of the product of the xy deviations divided by the square root of the sum of the squared deviations in x times the sum of the squared deviations in y. One thing that is important to note, correlation is always bounded between -1 and 1. So I could not have a correlation of -1.32. I could not have a correlation of 1.56. -1 is perfect negative. +1 is perfect positive. I can't get any better than that. So perfect correlation, here my correlation value is 1. So I've got perfect, I've got linear, and I've got positive. For strong, here I've got a correlation of approximately 0.95. So this is still positive, it's strong, it's linear. With this correlation of 0.75, notice it's getting a little bit harder to determine the trend. However, Notice that we have a positive sign on our correlation. That tells us we have a positive direction. We still have moderate. Ours is approximately 0.75, but we know we've got positive and we've got moderate, and this is linear. Another moderate, here I've got an elevation value of 0.6. I have positive, I have linear, I have moderate. Here I've got moderately weak. My correlation is approximately negative 0.25. Well, this tells me that I have a negative direction because I have a negative sign on my correlation. I have negative direction, linear, and moderately weak. Weak. I've got a correlation that is 0.15. This is a positive correlation. Therefore, I have a positive direction. So my direction is positive. My correlation is weak. And I can run a line through this. This is approximately 0. Very difficult to tell anything about this. All we can say is that, well, I can run a line through here, but it's not going to be very trustworthy. My correlation is approximately 0. Therefore, there's no correlation. So here, we've got positive direction, linear form, moderately strong, correlation's 0.85. Now, when we describe the relationship between the two variables, we need our scatter plot, which is going to show us our direction and our form and an idea of the strength. But among that strength, we need to make sure we include the correlation coefficient. So how do we get the correlation coefficient? Well, again, we said correlation between x and y was the sum of the xy deviations divided by the square root of the sum of the squared x deviations times the sum of the squared y deviations. So here I've got a data set that I'm going to go through. I've got my x is time on social networks, my y is GPA, and we'd like to see if there's a relationship between the time students spend on internet social networks and their GPA. First, we create our scatter plot, and this tells us, just by looking at the scatter plot, that we have got a negative linear, moderate to moderately strong correlation. Again, this is why we need our correlation value R. I said moderate to moderately strong. This is approximately negative 0.75. And we're actually going to go through and calculate this in a quick example. So here are my x values. Here are my y values. Here's my mean of x. Here's my mean of y. My deviations between x, my deviations between y. And so now what I need to do is take the deviations at x, multiply the deviations in y, sum those up. I get negative 7.900333. I square my x deviations, and I add them up, 29.40667. Square my y deviations, and I add those up, I get 2.768492. And so now I just go through and look at the sum of the deviations in x times the deviations in y, divided by, here I'm just plugging in the values that I saw on the last slide, my sums. So the sum of the square deviations in x, 29.40667, sum of the square deviations in y, 2.763492, and I get negative 0.8755901. That was a lot of work, though. There's an easier way to do this. Pearson's correlation coefficient can be written in the following manner. The sum of the xy's, x times y, minus n times x bar times y bar, divided by the sum of the xi squareds, minus n x bar squared, times the sum of the yi squareds, minus n y bar squared, and then we take the square root of this product. The sum of the xy's is 132.559, the sum of the x squareds, 215.06, sum of the y squared is 109.0355, x bar 3.9333, y bar 2.975833, x bar squared 15.47111, y bar squared 8.855584, and there are 12 values. And so when I plug these values in, I get negative 0.875587. And so our direction is negative, our form is linear, our strength is moderate to moderately strong, with R equal negative 0.8756. Okay, well, we'd like to see how to do an example like this in R, and so that's what we're going to look at now. I've created some data. Here I've got X, here I've got Y. I'm going to C-bind these into what I'm calling data XY. That way I can have X and Y side by side. First thing I want to do, I want to plot my data. And here is my plot of my data. Now it's clear that this is a positive relationship. It's also clear this looks to be relatively moderately strong. It's also clear that it looks like a line would fit through this very well. So how can we go through and calculate our correlation coefficient by hand? Well, remember, we said that the easiest way to do this was to take the sum of the xy's minus n times x bar times y bar, divided by the square root of the sum of the x squareds minus n times x bar squared times the sum of the y squared minus n times y bar squared. This is much easier than going through and getting all the individual deviations. And so this is how we're going to do this by hand. And so here I've got x bar as my mean of x. I'm just going to run all this. I've got x bar as the mean of x. I've got x bar 2 as the squared mean. I've got y bar, which is the mean of y, and then y bar 2 is the squared mean of y. Sx2 is the sum of the squared x values. Sy2 is the sum of the y squared values. Sxy is the sum of the xy's. Length of x is just how long is x? Well, there are 10 values in x. And so I'm going to set n equal to the length of x, which is 10. Now, the numerator, the sum of the xy's minus n times x bar times y bar. The denominator is the square root of the sum of the squared x's minus n times x bar squared times the sum of the y squareds minus n times y bar squared. And then I'm going to take numerator divided by denominator, and I'm going to call that R val. And R val in this case is going to be 0.9535719. Well, then this tells us that we've got a positive linear strong association. However, it would have been much easier to just use the correlation function. So I've got core xy here, and I get 0.9535719. This indicates positive, strong, linear. But remember, we do need both the scatter plot and the correlation value in order to be able to see the relationship and verify the strength. Okay, that's it for this video. This will end our introductory discussions of statistical methods and data analysis. In our next video series, we will start looking at probability and how we can use probability. See you then.